So in this class, I am going to explain how to verify the given displacement is an simple harmonic motion or not. So first I am going to start with, I am going to take the displacement x is equal to a cos omega t. Okay, so I am going to take plus phi naught. So this is my amplitude, omega is my angular frequency, 2 pi by t. Where this t is called your instantaneous time. Whatever the time you want to find the displacement vector, you can substitute that time. Okay, if you want to find the displacement of the particle at third second, you can simply put 3, then you can find. Then what is this phi naught? So this is the initial state of the system. Okay, if it starts from maxima, you can simply write cos theta. If it starts from mean position, you can simply write sine function. If it starts from in between, then you have to write this. Now this is going to be I will just take as a constant. Okay, I need not to worry about this phi. Okay, this is called your phase constant. So if you want to, I am going to write the expression here. What is that? D square x by dt square plus o. dt square plus omega square is equal to 0. This is a condition for simple harmonic motion. So I need the second order differential of the displacement. So I am going to take the first order differential. My velocity v is equal to dx by dt. So now we have a two differentiation. One is my time dependent parameters depending on first my omega is depending upon time, and then this cos theta is depending upon the time. First I am going to do differentiation for the omega t. So a omega, if I differentiate my cos, then I am getting minus of sine omega t plus phi naught. This is a constant. Omega is depending upon time and sine is depending upon time. In this case, the cos is depending upon time. Okay, so listen carefully. This is called your displacement amplitude. It's a maximum displacement from the mean position, right? And then this is a time dependent term. This a omega is called velocity amplitude. It's a maximum velocity of this oscillator, right? A is a constant, omega is a constant. It's a maximum displacement. So from hereafter the velocity will not increase. This is a maximum value. So the term before the time dependent term, it's called amplitude. In this case, it's called the velocity amplitude. Next, I just want to find the acceleration. So second order differential, my a equals to d square x by dt square. So I'm going to differentiate this. So if I differentiate this, first I am getting omega outside, minus of a will be there, already omega is there. If I bring this omega again, I am getting omega square. Sine differentiation again, cos of omega t plus phi naught, right? So a cos omega t is nothing but my x. So I can simply write minus omega square x. Agree? So in the left hand side we have a d square x by dt square. So d square x by dt square equals to plus omega square x is equal to 0. Now this obeys the simple harmonic condition. So the given displacement is a simple harmonic motion. In case here we have a omega square or 2 omega or t by 2, whatever the number, if there is any change, so I am not able to write my acceleration in terms of my x. So then your LHS is not equal to RHS. So this term is not going to be 0, which means whatever the displacement, which means my acceleration, the restoring acceleration, which is directly proportional to my displacement. Okay. Actually, in practical reality, it's not happening because there will be some friction, but that's a negligible friction. Okay, the day-to-day life it's not happening because there's a friction in the table, so we can neglect those things. Okay, so now I'm going to plot a graph between omega t versus x and omega t versus velocity and how that acceleration varies with respect to time. So this is a plot between omega t versus displacement. So the maximum displacement is going to be A. The negative max ought to be minus A. So here velocity versus omega t. So velocity versus omega t. So this is my amplitude, right? Here A omega is going to be a minus A omega. So velocity, amplitude, it's a maximum velocity. And then here is the acceleration versus omega t. So the maximum acceleration, this term. So this is time dependent term. The term before the time dependent term is called your amplitude. So this is called your acceleration amplitude, A max. Okay, A omega square is going to be minus A omega square. So this is my acceleration. Okay, so first I'm going to start with the displacement vector. If I take my phi naught is going to be 0. If my oscillator starts from maxima, then I can simply take, for simplicity, phi naught is going to be 0. Omega t, if I put t is equal to 0, if I start from 0, cos 0 patannam, cos 0, 1. So you are starting from at time t is equal to 0, you are in this position, right? Next, cos 90, 0. So you are moving from here to here. This is going to be pi by 2. So cos 180, minus 1. Minus of minus, okay, minus of plus, minus. You are moving from mean position to negative maxima, minus A. Okay. So again, cos 180, 0. So you are moving from here to 0. This is for pi, this is for 3 pi by 2. If I put cos 2 pi, 1. So you are in this position, right? Right? So this is at 2 pi. So this is called one full oscillation. The distance traveled from here to here is called lambda. It's called wavelength. It's a distance traveled by the wave in one oscillation. It's called wavelength. So now I'm going to compare how my velocity varies with respect to the same time period. So I can simply take this line here for the better comparison. Okay. So the displacement obeys cosine function, but the velocity obeys sine function. So sine 0, 0. You're starting from 0. Okay. Sine 90, but minus is going to be minus. So if I put sine 180, 0. Again, you're moving from here to here. Okay. Sine 270, minus 1. Minus of minus, plus. So plus maxima, and then sine. Again, it's going to be 0. When this is maxima, it obeys minima. Okay. Next, this is obeys the cosine function. My acceleration. Okay, this is acceleration versus omega t graph. Anyway, omega is going to be just a constant. Okay, omega is equal to 2 pi by t. Time period of the particular oscillator is going to be a constant. So actually, it's a graph between acceleration versus time, instantaneous time, right? So what's happening here? Cos omega t. If I put t is equal to 0, cos 0, 1, but minus a. You are starting from here. Okay. So if I put cos 90, 0. Cos 180, minus 1, minus of minus become plus. So you're moving from here to here. Cos 270, 0. Next, cos 2 pi. Plus 1, again. So this is your maximum acceleration, negative maxima. This is your positive maxima. So when it is oscillates, so we'll get this different graphs. Okay, so using displacement, velocity and acceleration graph, so we are able to find the position of the particle in the circular motion. So those things we'll discuss in the later class. Thank you.